Hello, and welcome to Badger Talks Live, which brings exciting happenings, resources, and talent from your UW flagship campus to the people of Wisconsin and beyond. I'm Chase Schultz from Cadillac, Michigan. I am a fifth-year graduate student who's studying physical chemistry. Specifically, I do gas phase rotational spectroscopy, and I am very pleased to introduce Susanna Widicus Weaver, Vozza Professor of Chemistry and Astronomy. Today, we will learn how molecules make up the world around us and serve as the building blocks to life as we know it on Earth. The questions remain as to how these molecules form and are incorporated into planets, and whether life might form elsewhere in the universe. Astrochemists study the chemistry of space and the evolution of molecules as stars and planets form. Let's dive into the work of the Widicus Weaver Astrochemistry Research Program, which incorporates laboratory spectroscopy, observational astronomy, and astrochemical modeling to decipher the chemistry that might lead to life in the universe. Susanna Widicus Weaver, the Vozza Professor of Chemistry and Astronomy, is an expert in prebiotic astrochemistry. Her research combines laboratory spectroscopy, observational astronomy, and chemical modeling, and is aimed at understanding the mechanisms driving interstellar chemistry and the pathways for the formation of life. She received a bachelor's degree in chemistry at Illinois Wesleyan University and her Ph.D. in chemistry at Caltech. She was a postdoctoral fellow in chemistry and astronomy at the University of Illinois from 2005 to 2008. And before moving to Wisconsin, she was a professor of chemistry at Emory University. Please welcome Susanna Widicus Weaver.
Thank you, Chase, for that wonderful introduction. I'm very excited to be here today to tell you a little bit about the work that Chase and my other students and I do here at the University of Wisconsin-Madison. So we study molecules in space. And I like to joke that we study little green molecules, though most of them are actually white. But these little molecules tell us what the chemistry of space might tell us about the possibility for life in the universe, and also how life might have arisen here on Earth. So I study objects like this one. This is the first image released from the James Webb Space Telescope of the Carina Nebula. This beautiful image came out last summer and just takes my breath away every time I see it. So this is a region of gas and dust in the interstellar medium, or the material between the stars. And if you see these regions where they're wisps, where it gets a little bit darker, a little thicker material, those are regions where there are stars starting to form. And my group actually studies these star forming regions, and we look at how the chemistry changes as we go from a cloud to a star, to a planet-forming disk, and then ultimately to other solar system like our own, where there might be evolved planets. We try to understand how that chemistry changes as those sources change through that process, and what that might tell us about the possibility for life elsewhere in the universe. So I mentioned this cycle of interstellar material. This is a beautiful graphic that explains how this happens. So we have those interstellar clouds like the Carina Nebula that we saw in that James Webb picture. And then eventually those undergo gravitational collapse to form star-forming regions. Once a new star forms, it starts to heat up in the material around it. We see a lot of chemistry in these star-forming regions. And those molecules that we see there are the building blocks of the solar system that will eventually form. That new star is still embedded in gas and dust, but eventually a disk forms around that star, and it's from that disk where we get planets, like our solar system. So you can see here in this image, a planet starting to sweep out material around the star. There's a lot of active work in astrochemistry right now, trying to understand how those planets form, how they incorporate material, how far away from the star they are, what the different masses are, and whether there could be other Earth-like worlds out there forming in other solar systems right now. And then from there, eventually those planets sweep out all the material in their orbit around the star, and you end up with a mature solar system like ours. And so we see the planets here, and those are orbiting a more evolved star. And from there, we can start to look at the atmospheres of those planets and understand that chemistry and what it tells us about whether there might be life elsewhere out there in the universe. So my group really focuses on this star formation phase, the second phase of this process, because it's there where the chemistry for life starts to turn on. And it's there where the material that gets locked into that solar system really forms. And that guides everything else that happens chemistry-wise after that point. We know that the material in the solar system is constantly getting delivered to planets. It constantly gets delivered to our own planet. So I show here a meteor shower image from the surface of Earth. This is material where usually from where we fly through debris left from the tail of a comet as it passes through, and that material rains down on the surface of Earth, and we see that in the form of a meteor shower. But we do have material make it all the way to the surface. So we can collect meteorites like this one I show here on the right. That's the Murchison meteorite, one of the most famous, because this dark material in the background here is all carbonaceous, and it takes carbon to build life as we know it. So it's there where the organic molecules that are the pieces of the early solar system are still trapped. And we can study that material and try to understand how life on Earth may have arisen. And so we can go out and collect these meteorites as they fall. We can take upper atmospheric flights and collect what are called interstellar dust particles, which are just the little debris left over that are making it into our atmosphere. And so there's this constant flux of material to the surface of Earth, all from space, all driving the chemistry on early Earth and even today, changing the chemistry that we see on Earth. If we take a step back and we look at what we can do with radio astronomy, this is a beautiful image from the ALMA Observatory, the Atacama Large Millimeter Submillimeter Array in Chile. This is one of the largest observatories on Earth because it's actually 66 antennas working together to take images of objects in space. And we use molecules as the guides to be able to take these images. So we can actually map the molecules in high resolution. So you see here one of these planet-forming disks. So there's a star in the center, and everywhere where you see a gap in the dust around that star is a region where a new planet is starting to form. And so we can actually use different molecules to trace the different chemistry. And I just saw some amazing results last week where we're getting to the point where we can actually use different molecules to image directly where the planets are forming in one of these disks. So exciting things to come, but this tells us that the chemistry that we see from interstellar clouds through the star formation and into the planet-forming disk is all related, and that tells us what's going on in our solar system and in other solar systems in the universe. So if we take a look at planets and we think about Earth, Earth is very squarely in what we call the habitable zone in our solar system, which means it's the right size and distance from the sun to be able to have liquid water at the surface. So if we want to look for a planet where there might be life elsewhere in the universe, we need it to be a habitable planet, which means we need it to, at a minimum, have liquid water available for life to have arisen the way we understand life on Earth. Beyond that, of course, we need organic molecules, we need access to surface carbon, we need a lot of the minerals that we need to support life, but at a bare minimum, you need liquid water. And so in our solar system, Earth is the only one completely in the habitable zone. Mars is right on the edge, and Venus is just outside. So Mars is a little too cold, and Venus is much too warm for there to be liquid water at the surface. But in other solar systems now, we're starting to pick up planets in this habitable zone. And now that the James Webb Space Telescope is operational, we can start to take spectra of those atmospheres, and we can tell if there is water in the atmosphere. We can look for oxygen, we can look for ozone, we can look for methane, which is a sign of bioactivity at the surface. And so people are constantly now collecting spectra of these other possible habitable worlds and trying to compare them back to what we see here on Earth. So there's some really exciting new things coming on board in the next few years in astrochemistry, because this exoplanet revolution is really going to change the way we think about the universe and our understanding of solar system building and how planets might form and how life might evolve. So in my group, we study the chemistry, and we try to understand how complex chemistry can become in space. So if we go from an interstellar cloud to a comet or a meteorite to an Earth-like planet, how does the material evolve as we go through that process? And can we form biomolecules? I show here glycine, the simplest amino acid used in biology here on Earth. Can we make glycine in space, or do we have to have an Earth-like planet for it to form? And that's an open question. We see glycine in meteorites and comets, but it has never been definitively detected in space. And so we're trying to understand these molecules, understand the chemistry at a very fundamental level, and then take the weird physical environments of space and try to predict what might form. So space is very cold, very, very cold, very low density, lower than the very best vacuum here on Earth. And so because of this, the chemistry changes. And so we see really bizarre molecules in space that you can't buy in a bottle here on Earth. But as you get closer and closer to a star-forming region and a planet-forming region, you actually see that chemistry become Earth-like. And so because of this, we know that the physics affects the chemistry. And we're trying to understand how the two interplay with each other and at what point along that pathway biology could turn on. So in my group here at Wisconsin, we do observations, but we also do laboratory work. So I have a brand new lab where we are taking spectra of molecules that are interesting for astrochemistry. And we are doing all sorts of interesting chemistry trying to take those spectra because, like I said, a lot of the really important molecules are things you can't actually buy in a bottle. So we do laser photolysis chemistry, which actually Chase, who introduced me, is working on that project. We also light up plasmas and look at molecules in those plasmas where we make ions or radicals. And then we actually can take spectra both of stable molecules and of these unstable molecules and use that as a guide to go and look for those molecules' fingerprints in space. So I compare two molecules here, both of which are important in space and important in prebiotic chemistry, methanol versus glycolaldehyde. And you can see that the patterns are very different. And that's based on the molecular structure. So we can actually use this as a fingerprint to go and look for each of those individual molecules in space. So when we take a spectrum at the telescope, we see everything all in one complex mixture. But if we have these laboratory spectra, we can disentangle that and pull out each molecule one at a time and understand specifically what chemistry is happening in that object. So as I mentioned, we also do observations. UW-Madison has an agreement with the Northern Extended Millimeter Array, or NOEMA Observatory, which is in the French Alps and shown here. We can use this array of telescopes not only to take spectra, but to take images. So I show on the left here an image of methyl cyanide in a star-forming region where there are actually two star-forming cores right next to each other, but they're different ages. If we zoom in on one of those cores, we can see all of these individual lines. And so we can piece through that with our lab data and understand which molecules are there. And we can also do imaging of the different molecules and understand how the source is forming and evolving and what the structure is. So this map on the lower right here is actually of formaldehyde in this source, the source on the right. We see formaldehyde in emission around the center of the source, but in the center of the source, we actually see it absorbing. That's because there's a dusty cocoon around that new star that obscures the molecules that we would normally be observing. And so because of that, we actually see this absorption in the dust. And so that's where that new star is embedded. And this is really exciting chemically because we're seeing organic chemistry happening in that dusty cocoon, which tells us that all of that material going into that star-forming region that will eventually lead to a disk that will make planets could contain biomolecules at the very basic, very introductory level of that organic chemistry. So more images and more science to come out of this. This is a wonderful partnership. Many in our department are actually doing very active research with NOEMA, and we're very excited to share these first results from my group. So I'm not alone at UW-Madison in being interested in astrochemistry and astrobiology. There are several colleagues in the chemistry department and the astronomy department that do various aspects related to this research. But very recently, we had a really exciting undertaking at UW-Madison to hire 3 new faculty members who study origin of life related questions. And so these three wonderful folks are coming on board. Batul Kachar's already here. She's in the bacteriology department. She studies ancient DNA and how early life on Earth may have evolved. Zoe Todd is joining us this fall as a new assistant professor. She studies the chemistry in the early solar system and how biological chemistry may have started on early Earth. And so she'll be here next month. And Thomas Beatty is in astronomy. He's been here for about a year. He studies those exoplanets, looks at their atmospheres, and looks for signs of biology on those external exoplanets and is trying to understand where life might be elsewhere in the universe. So I'm thrilled to have these new colleagues coming on board. And of course, all of my existing colleagues here at UW that do interesting science that overlaps with mine. We're building an interdisciplinary team called the Wisconsin Center for Origins Research, or WICOR. It's a collaboration with 7 UW-Madison departments: chemistry, astronomy, atmospheric and oceanic sciences, integrated biology, botany, bacteriology, and geosciences. We have space being remodeled in the astronomy department that will allow us to have collaborative meetings, workshops, and student training. And we're really excited for WICOR to get up and running because it's unlike any other collaborative center in the country, because it allows us to bring all of these experts from all these different disciplines together to learn from each other and do truly innovative, groundbreaking collaborative research. So the big questions that WICOR wants to answer, and the ones that drive my research: do other worlds offer habitable environments? Is Earth the only life-supporting planet in the universe? I think we can say definitively that that is not the case, but we're still trying to understand the chemistry on the other Earth-like planets that we found. How did life form on early Earth? That's a very tough question that many of my colleagues and I are trying to tackle. And then how did complex life evolve from those basic small molecules like I study in star-forming regions? And so now that we have this group and this collaborative effort in the center, we can start to answer these questions. And so we're now within reach of starting to tackle these big problems in science and understand our origins and origins elsewhere in the universe. So with that, I will stop and thank you all for your attention. This has been fantastic to be able to share my work. So that concludes my presentation for today. Feel free to post any questions in the chat, and thank you for listening.
Thank you for watching this Badger Talks live event produced by the University of Wisconsin-Madison through UW Connect's outreach and the Office of State Relations. Follow us on Facebook and YouTube to see the library of past recorded talks. Please visit badgertalks.wisc.edu to see the schedule of upcoming talks, sign up for the Badger Talks email list, and search the roster of over 400 UW experts who are available to give talks on important issues in your Wisconsin community.